Hello and welcome back. So in the last lecture, I introduced truth tables and I just gave you the truth table for each of our statement operators. And I told you, go home, memorize them, be able to write them out from memory, right? So I'm hoping that you are at that stage now. You know these truth tables like the back of your hand, because today we're going to learn what they're good for. What can you do with the truth table? So we've already created the truth tables for each logical operator. Um, we can also create truth tables for larger statements. So we've sort of seen that already because, for example, in our truth table for conjunction, we have each of the uh, atomic statements, right, P and Q, and then we also have a column for P and Q, right, for the conjunction. Well, we can do that. We can keep doing that, right, with more and more complex compound statements. So here's one. Statement is P and Q or not P, right? So in order to build a truth table for that, we're going to need columns for each of the parts, right? So you can sort of see on the furthest right column is the statement that I want to build the truth table for. And what I do is I kind of break it down by working backwards, right? So P and Q or not P is a disjunction, right? So I want to have a column for each of its disjuncts, right? So one of the disjuncts is not P, so I'll create a column for not P. And the other disjunct is P and Q, so I'll create a column for P and Q. And then each of those columns is also compound. I'll want to break those down as well. So not P is a compound statement, right? It's the negation of P. So we want to have a column just for P alone. And then the two atomic statements that feature in the column P and Q is P, which we already have, and Q, right? So we'll want a column for each atomic statement that features, and then a column for each part, right, of the compound statement. You kind of start at the right and break it down to the left, so that by the time you get to the left, all your left columns are atomic statements. So you'll notice that the P and Q, right, which we've already filled in the truth values, it's the same as the truth tables for any of our two-place operators like conjunction, disjunction, and conditional, right? If you fill out every possible combination of truth values, you'll end up with 4 lines, right? And anytime you only have 2 atomic statements, you'll have 4 lines. But if there's more atomic statements, right, if there's a P and a Q and an R, you would have to have more lines so that you could get every combination of truth values, right? And there's a general rule for how many rows you'll need depending on how many atomic statements you're starting with. And so if your number of atomic statements is n, you'll need 2 to the n rows, right? So here we have 2 atomic statements. 2 squared is 4, right? If you have 3 atomic statements, 2 to the third power is 8, right? If you had 4 atomic statements, 2 to the fourth power is 16, right? And it keeps doubling and doubling. I'm not going to give you problems with that many atomic statements because it just gets out of control. Right? But that is the general rule. In practice, we'll only have to deal with 8. I don't think I ever give you 16 rows, right? But that would be the most. Any more than that would be outrageous. So remember, for negation, right, there's only one atomic statement, so 2 to the 1 is 2. So you end up with 2 rows. Here is, on the right is the truth table for conditional, right? So we had conditional is a 2-place operator, so there's only 2 atomic statements we're dealing with. So 2 to the 2 is 4, so there's 4 rows. Here's one with 3 atomic statements, right? So P, Q, and R. So that'll be 2 to the third power, which is 8, right? So if we were trying to build a truth table for the compound statement, if P and Q, then if R, then Q, right? That is the statement all the way on the right. Since there's 3 sentence letters, right? 3 atomic statements that feature in that compound statement, I'll need to build a truth table with 8 rows. So here I am, and I've built it out. So So let's walk through. I've got all the truth values filled in here, but let me show you how I did that, right? And I think I walk you through it. So first of all, notice, right, when we have 8 rows, how do we fill out all the possible truth values for P, Q, and R? It's going to be different than the truth tables we've seen so far for all our two-place operators. So it actually is the same technique, it's just more of it, right? So you'll start with R, which is the rightmost atomic statement, right? Again, we're going to keep all our atomic statements on the left columns of our table. So underneath R, I'll alternate true, false, true, false, true, false. Under my Q's, I will then double that up. I'll go true, true, false, false, true, true, false, false. That's under Q. And then under P, I'll double that up once more, and I'll go true, 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 false, 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 right? And you can keep that technique, right? So you start by just alternating, and then you go 2 at a time, and you go 4 at a time, and if you had more, right, you go 8 at a time, 16 at a time, and so on. But we're not going to get that crazy, right? So that's how it's set up. Sort of the first 3 columns of my truth table is to just figure out what my atomic statements are. It's pretty easy, right? You just look at the compound statement on the far right. You say, well, what different letters show up? And P shows up, Q shows up, and R shows up. So that'll be your first 3 columns, and that's how you set up the truth values. You start with R, or whatever the rightmost atomic statement is, alternate true, false, then move to the left and go TTFF, TTFF, and then move to the left and go TTTTFFFF, right? More of it, it'll start to make sense. You'll get more practice. So I also need to figure out, so that's how we figure out how many rows there are, and that's how we fill in the rows for the atomic statements. How do I figure out how many columns there are going to be? Well, I have to sort of break down my compound statement, right? So on the far right, it's a conditional that I'm dealing with, so I'm definitely going to need a column for the antecedent, and then another column for the consequent, right? So that's what I have there. The antecedent is P and Q, so I have a column for P and Q all on its own, and then I have another column for if R then Q, right, all on its own. That's the consequent. And those are 2-place operators, and notice when I break those down, all that's left is atomic statements, and I already have the columns for all the 3 atomic statements. So that's all I need to do with this one, right? We end up with 6 columns and 8 rows. So now what do I do, right? I've got my columns set up, I've got all my rows set up, and I filled in my truth values for my atomic statements, right? Those get filled in from the beginning just according to a pattern. Well, now I have to start filling in the rest of them, right? So let's start with P and Q. So for that column, right, I look to my first row and I see on my first row, P is true and Q is true. Well, I know because I've memorized my truth table for conjunction that when both conjuncts are true, my conjunction comes out true, right? So I put a T in the first row under P and Q. Then I look at the second row. It looks on the second row, P and Q are also true, right? So once again, there'll be a T on the second row under P and Q. Now look at the third row. There, P is true, but Q is false, right? Well, I know from my truth table on conjunction that when one of the conjuncts is false, my conjunction turns out false. So on row 3 under P and Q, I have an F, right? And I'll continue to do that all the way down the line. And we'll notice that for all the rest of the rows here, P and Q, at least one of them ends up being false, right? So all the rest of my rows are going to be F's under P and Q. Let's look at the conditional, right? R then Q. So on row 1, I look at R and I look at Q. Notice they're in reverse order in this truth table. Sometimes that happens, right? So I have to remember which is the antecedent and which is the consequent, right? So R is the antecedent, right? And Q is the consequent here in column 5, right? So when I'm wondering what truth value to put in row 1 in column 5, I have to say, okay, if the antecedent is true and the consequent is true, right? Because in row 1 I have R being T and then Q being T, then the conditional comes out true, right? On row 2, R is false, right? And since R is the antecedent, we know that with a conditional, anytime the antecedent is false, the conditional comes out true, right? So on row 2 under if R then Q, I should put a T, right? Now look at row 3. Here, R, the antecedent, is true, and Q, the consequent, is false, right? Well, I know that according to my truth table for conditional, when the antecedent is true and the consequent is false, the conditional comes out false. In fact, that's the only time it comes out false. So I need to put an F there on that line, right? And I'll continue that way all the way down the column, right? Looking at the truth value of the atomic statements on that row and using my truth table for that operator to figure out what the resulting compound statement will be. So once I've filled out columns 4 and 5, now I can use those columns to figure out column 6, right? So column 6 is also a conditional. The antecedent is P and Q. Well, I've figured out the truth value for P and Q on row 1, right? It's true. And I've also figured out the truth value for the consequent, if R then Q. And that's in column 5 here, right? So now I can figure out the truth value for that whole conditional in 6. Well, true antecedent, true consequent, we get a true conditional, right? And in fact, it turns out that, right, if we look down our columns, there's never actually a situation where P and Q is true and if R then Q is false, right? So it seems to always be the case that the conditional, if P and Q, then if R then Q, right, the column 6 there, it always comes out true, right, in our truth table. That means this is a tautology, right? It's a statement that is always true. It's logically true. So this is telling you how to build up the truth table, right? So I've already explained this and we can walk through it again, right? So again, your atomic statements, you want to start with the rightmost atomic statement here. It's R, go true, false, true, false, true, false. Then you move to the left to Q, double it up, true, true, false, false, true, true, false, false. Then move to the next one, double it up again, 4 trues, 4 falses, and so on. Then we fill in the compound statements, right, that are the part of the larger compound statement that we want to figure out the truth value for. We find that it's got an antecedent and a consequent, P and Q, and R then Q. So then we've broken it all down and we fill in the truth values. And this turns out to be a tautology, right? That means that this statement will always come out true, no matter what the truth values of the atomic statements, right? That means this statement can't be false. It's logically true. So it could be something like this, right? If we wanted to sort of like, again, any statement with this structure would be true. We could kind of fill it in with any sort of English sentence. So if it was something like this, if you clean the kitchen and go to the movies, then if you read the newspaper, you go to the movies, right? Now that seems sort of weird, but basically it's saying, look, the antecedent already says you go to the movies, right? Therefore, whatever else you do, you're going to the movies, right? That's basically what it says, right? These tautologies are not particularly informative, right? They're not giving you new information. They're logically true, but that's just the way tautologies are, right? For example, it's raining or it's not raining, right? P or not P. That's logically true, right? Because either it is or it isn't, right? And it's a disjunction. So one of those is going to be, one of those disjuncts is going to be true, and a disjunction is true as so long as one of the disjuncts is true, right? Or P and not P. Right? I can't be a professor and not a professor, right? Something like that. Right? Not the case that P and not P. That would be logically true as well. That's a tautology. So sort of the opposite of a tautology is a contradiction. Some statements are false no matter what the values of the atomic statements. Let me give you a simpler one because that was a pretty complicated one because I needed to teach you how to build the larger truth tables because we'll use those for other purposes as well, right? But just to illustrate contradiction, let's make it a little more simple. P and not P, right? It's raining and it's not raining. I'm a professor and I'm not a professor. That's just a false statement no matter what. And it's fairly obvious if you look at the truth table, right? So first we start at the right with the complete compound statement. It's P and not P. It's got two parts, right? Not P being one of them, P being the other. So we create columns for those. Not P, if we break it down and get rid of the operator, we end up with P. We already have a column for P. So that's our whole truth table, right? So our only atomic statement is P, so we only need two rows, right? 2 to the 1. And TF, that's every combination of truth values for the atomic statement P. And then we can start to build out our truth table. So in row 1, if P is true, then not P will be false, right? That's how negation works. And if P is true, not P is false, then the conjunction of P and not P will come out false, right? Because any conjunction with one false conjunct is false. Well, let's suppose P was false. Then what would happen? Well, not P would be true, right? And then if you can join them together, you'd still have one false conjunct, and so the whole statement will come out false. So no matter what the truth value of P and not P will come out false. That is a contradiction, right? It comes out false no matter what the truth values of the atomic statements. While we're at it, right, we've seen tautologies and contradictions. There's a third type of statement called a contingency. Those types of statements can be true, might be false, depending, right? So, for example, if I just said P and Q, right, it's raining and my foot hurts, sometimes that might be true, sometimes that might be false, right? If we break it down, do the truth table, right? So it's P and Q, right, goes in the right column, and then we start to break it down. Well, it's only got two atomic statements, right? And it's a single operator, so it's easy to break down. We need a column for P, a column for Q. So we know how to fill in the truth values for those, right? We've got two atomic statements, right? So we need 4 rows, right? 2 to the 2. We start with the rightmost atomic statement, Q, and we alternate true, false, true, false. Then we move to the left to P, and we go T, T, F, F, right? So now we've filled in all the possible truth values for our atomic statements, and now we can use those to figure out the truth value of the conjunction. Well, let's look at row 1. If P is true and Q is true, then P and Q will also be true, right? A conjunction with 2 true conjuncts comes out true. Look at the second row. P is true and Q is false. Well, that conjunction is going to come out false. And in fact, all the other ones are going to come out false because one of the conjuncts is false. So it looks like P and Q is sometimes true and sometimes it's false. So it's called a contingency, right? It's neither a tautology or a contradiction. It's contingent, depending on whether it is actually raining or my foot actually hurts, then it would be true. Otherwise, it's false. So we've seen one thing we can do with truth tables. We can use it to determine whether a statement is a tautology, right? True all the time, a contradiction, false all the time, or a contingency. Sometimes true, sometimes false, right? There's many other things we can do with truth tables. We can check an argument for invalidity, right? So we already had one technique for checking arguments for invalidity, the counterexample, right? And the truth table method is sort of similar, right? So remember, a counterexample was a situation where the premises are true, but the conclusion is false, right? So we had, if Felix is human, then Felix is an animal. Felix is an animal, therefore Felix is human. Well, that turned out to be invalid because we can imagine a counterexample. If Felix is a dog, premise 1 will still be true, premise 2 will still be true, but the conclusion will be false, right? Felix is not human. We can also do this using a truth table. The reason a truth table would be helpful, right, is because it's a algorithmic, right, procedure where you don't have to worry about whether you were clever enough to come up with an example, right? If you can fill out the whole truth table, you have a rigorous decision procedure for determining invalidity and, as we'll see, validity as well, right? So you can kind of imagine why that's the case, right? As you see what truth tables are doing, they're covering every possible truth value of every possible atomic statement and then telling you what happens, right? So you can do that with an entire argument as well. right? So if you end up with a line, right, where the premises are true but the conclusion is false, then you'll know that the argument's invalid. And if you can't come up with such a line, well, you've covered every possibility. So you know there's no way it turns out invalid, and so it must be valid, right? So let's start from scratch with an argument in English, right? And we'll work through it, build a truth table, and assess it for validity. So here's our argument. Either Jones was at the beach or Jones was at the crime scene. If Jones was at the crime scene and the glove fits Jones and the gloves fit Jones, then Jones is the murderer. Jones was not at the beach. The gloves fit Jones, therefore Jones is the murderer. So you can imagine it trying to come up with a counter using the counterexample method might be a little sort of mind bending, right? There's so many premises going on that trying to figure out a situation where they all come out true and the conclusion is false might be a little tricky, right? So instead, we could use the truth table method. Now, first we need to symbolize, right? We need to translate the argument into a logical notation, right? So we can start with premise one, right? Either Jones was at the beach or Jones was at the crime scene, right? So we could, that's just a disjunction. So we could translate that as B or C, right? The second sentence is a conditional. If Jones was at the crime scene and the gloves fit Jones, then Jones is the murderer. So it looks like the antecedent of that conditional is a conjunction, right? So you could translate that whole thing as if C and G, then M. Sentence four, right? The fourth premise, Jones was not at the beach. Well, that's just a negation, right? So it'd be something like not B, and then the gloves fit Jones. Well, that's just atomic, so that premise would just be G, right? And then the conclusion, Jones is the murderer, also just atomic, so M. Right? So we have four premises and a conclusion. All right, we've translated the argument, right? Now to set up our truth table. So first of all, we have to figure out how many atomic statements there are. I see a B, I see a C, there's a G, and an M, and it doesn't look like there's anything else. So there's four atomic statements that feature in this argument, right? So on the left, we'll need a column for each of those four, and we also know that the number of rows we'll need will be 2 to the 4, right? So 16 rows. So getting a little crazy here. I won't make you get this crazy on homeworks or exams, but you know, this is a lecture. Let's get a little nuts, right? I'll show you how complex it could be, and then on your own. So 16 rows, right? We'll put our atomic statements there. It doesn't really matter what order you put the atomic statements. And notice that the orders of the columns is going to have to be different than the order of the premises, because our conclusion is an atomic statement, M. One of our premises is also an atomic statement, G. So those are going to have to show up in the first four columns, right? So they're out of the order they're in the argument. That's fine. It doesn't cause a problem for the truth table. It sometimes makes reading it a little tricky, but not a big deal. So we've got our four atomic statements in the first four columns. So we have to set up every combination of truth values, and we can do that using our same procedure. So we start with the rightmost atomic statement here, that's M, and we just alternate TF, 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 TF all the way down that fourth column. Then we move one column to the left to the third column, and there we double up true, true, false, false, true, true, false, false, all the way down. Move one more to the left to C. There we go, 4 true, 4 false, 4 true, 4 false. And then all the way to the left to the first column, B, and we do 8 trues and then 8 falses, right? So if there had been 32 rows, right, there would be another column and it would be 16 trues and 16 falses. But I would never make you do that, right? But again, this procedure can be extended indefinitely. Okay, so we've got our first 4 columns set up. So how do we set up the rest? Well, we want to set it up in sort of an increasing complexity, but to figure out exactly what we need, I would then jump to the far right and build a column for your the longest statement that you might have, the most complicated one. There, that's if C and G, then M, right? So That's a conditional, but it's got some parts that are compound statements, right? So definitely C and G needs its own column, right? So we'll put that in its own column to the left. That one then can be broken down into C, right? C's got its own column, G, that's got its own column. The consequent of there, M, that's got its own column. So that statement is pretty well broken down. What else do we need? Well, we've got a premise. This premise 1 says B or C, so let's make a column for that. Again, there's no strict rule as to where you place your columns. They put your atomic statements on the left and then try to build up an order of complexity as you go to the right. But sometimes there's no strict rule, like what's more complex, B or C and G? It doesn't really matter. It'll work out fine either way, right? So we got a column for that. But we definitely need a column for each premise, right? And then a column for all the parts of that premise that needs to be broken down, and a column for your conclusion as well. So we got another premise that's not B, just the negation of B, and we already have a column for B. So it looks like we've got columns for all of our premises, for our conclusion, and then all of the parts of those premises and conclusions. So now we can just start filling out the truth table. So again, right, our conclusion is atomic statement, so we can't put that in the end. So our premises are sort of jumbled, right? We have premise 4 in column 3, then we have the conclusion, then we have premise 3, then we have premise 1, then we have premise 2 at the end. The way the truth tables are set up is not always the same as an argument is set up, but that's fine, right? And you might think, is it weird to like assign truth values to the conclusion before I've even like assigned the premises? Don't you figure out if the premises are true and then the conclusion? Well, that's not the point of the truth table, right? We're trying to figure out if the argument is valid, right? Which means we're trying to figure out if when the premises are true, the conclusion always has to turn out true, right? And so we're figuring out every possible combination. What's every way this could go? And we'll see if there's, with an exhaustive list of all the possible combinations, is there any situation where the premises are true and the conclusion is false? If so, argument is invalid, right? Because that's the definition of validity, is it's impossible for the premises to be true and the conclusion false. So you can think of this as we're looking for a counterexample here, and we can construct a counterexample using the truth tables, right? So let's keep moving with that. So let's start moving to the right and just filling in our truth tables. So we had the first 4 already set up, our atomic statements. So our first compound statement is column 5, premise 3, not B. Well, that's just a negation, right? So we'll look over at B, and on row 1, B is true. So that means in the column under not B, we should put a false, right? Because that's how the truth table for negation works. Right? If P is true, not P is false. And that's going to be the case on row 2, 3, 4, 5, all the way through 8, right? Because we've got P's on the first 8 rows under B. So on the first 8 rows under not B, we should put F's, right? Then at row 9, we switch under B, right? In the first column there. And then they're all F's. So every time there's an F for B, we should write a T for not B, and so on. So you'll notice that the column for not B is just sort of the mirror image of the column for B. All right, we've filled out the column for not B, so let's keep going. Premise 1 here, the next column, B or C. So that's a disjunction, right? So we need to look to the columns for B and the column for C. On the first row, B is true and C is true. Well, a disjunction with 2 true disjuncts comes out true, right? So we'll put a T under B or C on that row. And it looks like for the first 4 rows, B and C are both true. So for the first rows of B or C, first 4 rows of B or C, we should put in a T, right? Around row 5, things start to change a little bit. Looks like we've got B being true and then C being F on row 5. Well, with the disjunction, that still comes out true, right? As long as one of the disjuncts is true, the whole disjunction is true. So we'll keep putting T's in the B or C column, right? And you'll notice around, down around row, what is that, 9, I guess? we have B being false under the B column and C being true. And that still is a true disjunction, right? Because one of the disjuncts is true. So we keep filling out T's in the B or C column. Finally, in the last 4 rows, we notice that B is false and C is false, right? And if both disjuncts are false, then we definitely have a false disjunction. So in those last 4 rows, B or C is going to turn out false. Let's move on to C and G. Now this isn't a premise, right? But we needed a column for it because C and G is the antecedent of premise 2, right? So we have to figure out that truth value before we can evaluate the truth values of premise 2. Let's figure that out. So C and G, well, let's look at the column for C on row 1 and the column for G on row 1. Fortunately, they're next to each other. That's always helpful. We have TT, so a conjunction with 2 true conjuncts will be true. So we'll put in a T right under on the first row for C and G for column 1, 2, 3, 4, 5, 6, 7 there. And we keep going down, right? So again, row 2, we get TT for C and G, so that'll be a true for the conjunction. On line 3, C is true, but G is false. Well, a conjunction with 1 false conjunct is going to come out false. So we're going to have to fill in a false under the C and G on row 3. And so on down the line, right? So you just follow your truth table for conjunction, look at your 2 conjuncts. If they're both true, fill in a T. And if any one of them is false, then you put a false under C and G. And so we're down to our last column, right? And remember, it's not our conclusion. It just happens to be our most complicated statement, which is premise 2. So that's how it ended up last. But let's fill that one in, and then we can start assessing the argument for validity. So if we're filling in the last column, it's a conditional, right? So we have to remember our truth table for conditional. We need to look at the column for the antecedent, which is C and G, and then the column for the consequent, which is M, right? So on row 1, C and G is true, and M is true, right? So true antecedent, true consequent, that's a true conditional. Right? What about row 2? C and G comes out true, right? And M is false on line 2. Well, true antecedent, false consequent, that is a false conditional, right? Put an F on row 2 of the last column. Now, you can sort of start to, once you get used to conditionals, do little shortcuts, right? So you could just look at the antecedent, C and G, and you'll know, if you know your truth table for conditional well, that anytime the antecedent is false, the whole conditional comes out true, right? So you could just go down your column for C and G, and every time it's F, just hop over a column and fill in a T, right? So on lines 3, 4, 5, 6, 7, and 8, right, C and G is false, and since that's the antecedent, you know the whole conditional will come out true, right? And the only ones you have to look a little more carefully at are the ones where the antecedent is true, because a true antecedent and a false consequent gives you a false conditional. And that does happen a few times. It happens on line 2 and then again further down. So now we've filled out all the columns for our truth table. Now we can assess our argument for validity. So again, we're looking for a counterexample row, right? Is it possible, given all the possible combinations of the truth values, for the premises to be true and the conclusion false, right? Well, it'll help us to first just look at the row for the conclusion, and we can ignore any rows where the conclusion is true, right? Because that's not going to be a counterexample. But every other row is a situation where the conclusion is false. So let's check. Row 2, right? The conclusion is false. Let's look at our premises. Well, it looks like 1 is true, 2 is false. Well, we already know that's not a counterexample, right? A counterexample is all true premises and a false conclusion. So if you see a false conclusion, but then you're checking around your premises, and as soon as you find a false premise, that row is not going to be in a counterexample. So move on to the next false conclusion. That'll be on line 4, right? Okay, premise 1 turns out true, premise 2 is true on that line, right? Oh, but premise 3 is false on that line. So that's not a counterexample either, right? And you can go down, right, the whole truth table looking for a counterexample with all true premises and a false conclusion, and you're not going to find one, right? This is a valid argument, right? And, try it for yourself, right? Practice, right? Say, okay, you could do it one row at a time. Say, let's look at all the premises, true, true, true. Oh, the conclusion comes out true, so that's not a counterexample, right? Oh, this one's true, but there's a false premise. That can be a counterexample, right? Check them all, right? So after you've checked them all, you will find that there is not a single row where all the premises are true and the conclusion is false, which means there is no possible situation where the argument is invalid. So that must mean the argument is valid, right? So this is a way of checking for validity. It's a pretty boring and fiddly one, and you can see how easy it would get at a certain point to have your eyes cross and forget and confuse an F with a T, right? So again, on quizzes and exams, I'm not going to give you anything this ugly, right? But also it's just pretty boring. So, practice this, master this, and then I'm going to give you the proof method of checking for validity, which is a little more fun, if you have the sort of brain that I have, and I think some of you will probably find that it's fun for you as well. But for now, let's just learn this truth table method for checking for validity, checking for whether a statement is a tautology or a contradiction or a. So back to the argument. So it turns out it is a valid argument, right? And the conclusion was Jones is the murderer. So should we convict Jones? Well, again, not yet, right? A good argument where the conclusion is guaranteed to be true is not just a valid one, it's got to be sound, right? And if you'll recall, a sound argument is valid plus true premises, right? So once we've checked the argument for validity and it's valid, but we still need to check the premises for truth, right? So, we don't know which, if all the premises are true, right? One of the premises was Jones was not at the beach, but maybe that's false. Maybe he was at the beach, right? Or there was a disjunction that said, hey, either Jones is at the beach or at the crime scene. Well, maybe that disjunction is false. Maybe there's a third place he could have been, right? And a good lawyer who's trying to defend, or actually who's trying to convict Jones, would try to give you good reasons to believe each of those premises as well. And if you can be convinced of the premises, then you should convict Jones because the argument is certainly valid. Right? All right. So again, practice the homework with the truth tables. Come talk to me in office hours if you need to. We'll stay in touch. I'll post the homework, answers to the homework after it's due, so you can check your answers. And again, with all of these, every lecture I'm going to be telling you practice. That's how you get this stuff. It's got to be in your bones, right? All right. Well, I will see you next time.